Hello everyone, and welcome to my channel. This is an educational channel, and we look at great theories of everything, including the reciprocal system of theory from Dewey B. Larson. And today is our 478th video that we've done on the reciprocal system, going deep into several of his books and many articles by both Larson and some of his associates and students, so to speak. And today we are looking at his book called Basic Properties of Matter. And he wrote this in 1987, just 3 years before he died. And we're in chapter 9 on electric currents. Basic Properties of Matter is a book primarily on chemistry. But as Larson is the author of a theory of everything, a theory of general application in the reciprocal system of theory, the ramifications of his books on chemistry, on temperature, pressure, electric current, and so forth, can be applied to many other fields. And so we're looking at these books kind of to get analogies, and also to just kind of understand how he's thinking about these things, how he goes about his business, and how we can go about our business, because the reciprocal system is a system of theory. So you can, once you understand how the system works, you can plug it into any subject that you want. So you can plug it in. It kind of democratizes, if you want to use that word, which maybe I shouldn't, but it makes accessible science to the layperson. If they are studious and they, get their act together, then they can start doing science with the reciprocal system. And it shows because Larson, by himself, was able to, in studies like Basic Properties of Matter here, Larson arrived at two fundamental postulates in 1959, and then from there he arrived at a theoretical universe, what the universe would look like if his postulates were correct. This is strictly from theory. And then in his books, he compared his theoretical universe with the actual so-called measured, empirical, and compiled universe of the legacy scientists. What, products that required an army of scientists, trillions of dollars over centuries of time. And Larson was more or less able to recreate what they had come up with over all that time by himself with a slide rule on his living room chair. So this does show how, science is, through the reciprocal system, science can be back into the hands of the layperson, the, hardworking layperson. This isn't an easy thing to understand, but you can have the motivation to understand it, because you can understand that if I do understand this, I understand the basis for everything, and I can plug this into anything. Now, the basic ins and outs of the reciprocal system, I went through over and over and over again in the first 474 videos that I've done on this topic. And so if you don't understand how the reciprocal system works, refer to one of those videos. Today, we're going to go right into the reading from chapter 9 and pretty much assume that you at least have a working knowledge of the reciprocal system. I will try to clarify certain issues as they come along in the text. But I'm trying to be focused on like turning some pages here and like actually getting through this work that I'm trying to read into the record without taking 2/3 of the video just to give you background information over and over and over again. I've done it, like I said. I think I provided a pretty thorough explanation of the reciprocal system, at least for introductory purposes, on 474 occasions. And so I frankly feel like I've said what I'm going to say about that for now. Maybe I'll go back and sum it up later, because I'm always learning more about the reciprocal system and I'm always understanding more. And so hopefully my general knowledge advances and I might be able to summarize it better in the future. But for right now, we're going to be just getting right into the text. And this is coming from chapter 9. Larson had just gotten done talking about, let me just read this last sentence from the paragraph before. But where the atoms of a material aggregate are in effective motion thermally, movement of electrons through the matter adds to the spatial component of the thermal motion. That is, it increases the speed and thereby imparts energy or heat to the moving atoms. And he's really, saying that the electric current does not heat the atom up if there is no space component to your atom, meaning more or less that there's no heat there, and that's why superconductivity operates at very cold temperatures. But basically, the main point that he got to at the beginning here is that the electric current comes from electrons, and in particular, it comes from uncharged electrons, which goes against legacy science, who believe all electrons are charged. Larson has a charged and an uncharged electron. An electron is simply a rotating unit of space, which makes it somewhat unique. It's kind of a world of space in this world of time, which is the atom. And so because the relationship between space and time is motion in Larson's system, this is the fundamental of Larson's system. The universe is made out of motion, and motion is the relationship between space and time. Because the uncharged electron is made out of space, it's a rotating unit of space, it moves through matter, because matter is primarily made out of time. And so the relationship between space and time is motion. So the electron moves through matter, and that is called electric current. And it moves through the matter kind of based on some of the characteristics of that matter. Some forms of matter are more time. Some have some spatial components as well. And that kind of makes the difference between what you would call a conductor and an insulator. And I think you'll get to that coming up later. So let's start here. The magnitude of the current is measured by the number of electrons, or units of space, per unit of time. So that's how you measure current. Number of electrons, or number of units of space per unit of time. And again, Larson's system is quantized. Everything comes in units. You have to have a full unit of something before you have something. Units of space per unit of time is the definition of speed. Hence, the electric current is a speed. From a mathematical standpoint, it is immaterial whether a mass is moving through extension space, or space is moving through the mass. Thus, in dealing with the electric current, we are dealing with the mechanical aspects of electricity. And the current phenomena can be described by the same mathematical equations that are applicable to ordinary motion in space, with appropriate modifications for differences in conditions where such differences exist. It would even be possible to use the same units, but for historical reasons and as a matter of convenience, a separate system of units is utilized in present-day practice. The basic unit of current electricity is the unit of quantity. In the natural system, it is the spatial aspect of one electron, which has a speed displacement of 1 unit. Quantity, Q, is therefore equivalent to space, S. Energy has the same status in current flow as in the mechanical relations, and has the space-time dimensions T over S. And remember, Larson has a system where all of our scientific phenomena are relationships between space and time and can be notated with fractions, time over space or space over time, with the caveat that time and space can have exponents. Energy divided by time is power, 1 over S. Energy is T over S divided by time. T over S over T is 1 over S, power. A further division by current, which has the dimensions of speed, S over T, then produces electromotive force, EMF, with the dimensions of T over S times 1 over S times T over S equals T over S to the second power. These are, of course, the space-time dimensions of force in general. Force is T over S squared. The term electric potential is commonly used as an alternative to EMF, but for reasons to be discussed later, we will not use potential in this sense, where a more convenient term than EMF is appropriate. We will use the term voltage, symbol V. Dividing voltage, T over S squared, by current, S over T, we obtain T squared over S to the third. This is resistance, symbol R. The only electrical quantity thus far considered that is not equivalent to a familiar mechanical quantity. Its true nature is revealed by an examination of its space-time structure. The dimensions T squared over S to the third are equivalent to mass, T to the third over S to the third, divided by time, T. So resistance is basically mass divided by time, mass per time. Resistance is therefore mass per unit time. The relevance of such a quantity can easily be seen when it is realized that the amount of mass entering into the motion of space, or electrons, through matter is not a fixed quantity as it is in the motion of matter through extension space, but a quantity whose magnitude depends on the amount of movement of the electrons. In motion of matter through extension space, the mass is constant while the space depends on the duration of the movement. In the current flow, the space, or the number of electrons, is constant while the mass depends on the duration of the movement. Which is the same. Yesterday, in the intro to this chapter, Larson did talk about how the movement of space through matter, or electrons through matter, is the reciprocal or analogous to the movement of matter through space. So think of matter moving through space, and then its reciprocal would be the movement of electrons through matter. And so here he's showing how those are parallels. This is also a very good illustration of how Larson's system of units, where everything has units of space and time only, space over time or time over space, with exponents only, without the mass of the MKS system, or the kilograms of the MKS system, makes everything a lot more easy, and it also clarifies relationships. You can understand much more clearly what you're dealing with when you understand the units of something. You can understand what those units are really all about, whereas when you're using the MKS system, it's a lot more opaque. Okay. If the flow is only momentary, each electron may move through only a small fraction of the total amount of mass in the circuit, whereas if it continues for a longer time, the entire circuit may be involved repeatedly. In either case, the total mass involved in the current flow is the product of the mass per unit time, the resistance, and the time of flow. In the movement of matter through extension space, the total space is determined in the same manner. That is, it is the product of the space per unit time, or velocity, by the time of movement. In dealing with resistance as a property of matter, we will be interested mainly in the specific resistance, or resistivity, which is defined as the resistance of a unit cube of the substance under consideration. Now recall, a lot of times when Larson is, got his universe of motion, and many of his key units involve the rates. Okay, so he's not wanting to know as much about resistance as what he would call specific resistance. You remember in earlier chapters here in this book, we learned about specific rotation, specific heat, so this is having to do with the rate of something. So this is resistivity, which is defined as resistance of a unit cube of the substance under consideration. Resistance is directly proportional to the distance traveled by the current and inversely proportional to the cross-sectional area of the conductor. It follows that if we multiply the resistance by unit area and divide by unit distance, we arrive at a quantity with the dimensions t to the second over s to the second. That reflects only the inherent characteristics of the material and the environmental conditions, principally temperature and pressure, and is independent of the geometrical structure of the conductor. The reciprocals of resistance and resistivity are conductance and conductivity, respectively. With the benefit of the clarification of the space-time dimensions of resistance, we can now go back to the empirically determined relations between resistance and other electrical quantities and verify the consistency of the space-time identifications. Okay, voltage. That is V equals IR. And in Larson's system, voltage is IR, current times resistance. That's S over T times T squared over S to the third, which equals T over S squared, which are the units of force. So voltage is a force. Power equals I squared R. That is current to the second power times R times resistance. So power equals S to the second over T to the second times T to the second over S to the third equals 1 over S, power. Energy equals current squared times RT. Current squared times resistance times time. And that is S squared over T squared times T squared over S to the third times T equals T over S. Energy is T over S. This energy equation demonstrates the equivalence of the mathematical expressions of the electrical and mechanical phenomena. Since resistance is mass per unit time, the product of resistance and time, RT, resistance times time, is equivalent to mass, M. The current, I, is a speed, or velocity. The electrical energy expression, RT, I squared, is thus dimensionally equivalent to the kinetic energy expression 1/2 mv squared. In other words, the quantity RT I squared is the kinetic energy of the electron motion. Instead of using resistance, time, and current, we may put the energy expression into terms of voltage, equivalent to current times resistance, and quantity, Q, equivalent to current times time. The expression for the magnitude of the energy, or work, is then work equals voltage times the quantity. Here we have a definite confirmation of the identification of electric quantity as the equivalent of space. Force, as described in one of the standard physics textbooks, is an explicitly definable vector quantity that tends to produce a change in the motion of objects. Electromotive force, or voltage, conforms to this description. It tends to cause motion of the electrons in the direction of the voltage gradient. Energy in general is the product of force and distance. Electrical energy, as VQ, is the product of force and quantity. It follows that electrical quantity is equivalent to distance, the same conclusion that we derived from the nature of the uncharged electron. In conventional scientific thought, the status of electrical energy as one form of energy in general is accepted, as it must be, since it can be converted into any of the other forms. But the status of electrical or electromotive force as one form of force in general is not accepted. If it were, the conclusion stated in the preceding paragraph would be inescapable. But the clear verdict of the observed facts is disregarded because there is a general impression that electrical quantity and space are entities of a totally different nature. The early investigators of electrical phenomena recognized that the quantity measured in volts has the characteristics of a force, and they named it accordingly. Contemporary theorists reject this identification because it conflicts with their views as to the nature of the electric current. W.J. Duffin, for instance, gives us a definition of electromotive force and then says, in spite of its, quote, in spite of its name, it is clearly not a force, but is equal to the work done per unit positive charge in taking a charge completely around the electric circuit. Its unit, therefore, is the volt. End quote. Work per unit of space is force. This author simply takes it for granted that the moving entity, which he calls a charge, is not equivalent to space, and he therefore deduces that the quantity measured in volts cannot be a force. Our finding is that his assumptions are wrong, that the moving entity is not a charge, but is a rotating unit of space, an uncharged electron. The electromotive force, measured in volts, is then, in fact, a force. In effect, Duffin concedes this point when he tells us in another connection that, quote, V over N, volts per meter, I don't know why the N is there, but maybe it's an M, I'm not sure. V over N, volts per meter, is the same as newtons per coulomb. Both express the voltage gradient in terms of force divided by space. Okay, the quote, the actual quote is V over N, volts per meter, is the same as newtons per coulomb. And then Larson goes on and says both express the voltage gradient in terms of force divided by space. Conventional physical theory does not pretend to give us any understanding of the nature of either electrical quantity or electric charge. It simply assumes that inasmuch as scientific investigation has hitherto been unable to produce any explanation of its nature, the electric charge must be a unique entity, independent of the other fundamental physical entities, and must be accepted as one of the given features of nature. It is then further assumed that this entity of unknown nature that plays the central role in electrostatic phenomena is identical with the entity of unknown nature, electrical quantity, that plays the central role in current electricity. The most significant weakness of the conventional theory of the electric current, the theory based on the foregoing assumptions, as we now see it in the light of the more complete understanding of physical fundamentals derived from the theory of the universe of motion, is that it assigns two different and incompatible roles to the electrons. These particles, according to present-day theory, are components of the atomic structure, yet at least some of them are presumed to be free to accommodate themselves to any electrical forces applied to the conductor. On the one hand, each is so firmly bound to the remainder of the atom that it plays a significant part in determining the properties of that atom. And a substantial force, the ionization potential, must be applied in order to separate it from the atom. On the other hand, these electrons are so free to move that they will respond to thermal or electrical forces whose magnitude is only slightly above zero. They must exist in a conductor in specific numbers in order to account for the fact that the conductor is electrically neutral while carrying current, but at the same time, they must be free to leave the conductor either in large or small quantities if they acquire sufficient kinetic energy. It should be evident that the theories are calling upon the electron to perform two different and contradictory functions. They have been assigned the key position in both the theory of atomic structure and the theory of electric current, without regard for the fact that the properties that they must have in order to perform the functions required by either one of those theories disqualify them from for the functions that they are called upon to perform in the other. In the theory of the universe of motion, each of these phenomena involves a different physical entity. The unit of atomic structure is a unit of rotational motion, not an electron. It has the quasi-permanent status that is required of an atomic constituent. The electron, without a charge and without any connection with the atomic structure, is then available as the freely moving unit of the electric current. The fundamental postulate of the reciprocal system of theory is that the physical universe is a universe of motion, one in which all entities and phenomena are motions, combinations of motions, or relations between motions. In such a universe, none of the basic phenomena are unexplainable. Quote, unanalyzables, as Bridgman called them, do not exist. The basic physical entities and phenomena of the universe of motion, radiation, gravitation, matter, electricity, magnetism, and so on, can be defined explicitly in terms of space and time. Unlike conventional physical theory, the reciprocal system does not have to leave its basic elements cloaked in metaphysical mystery. It does not have to exclude them from physical inquiry in the manner of the following statement from the Encyclopedia Britannica. Quote, the question, what is electricity, like the question, what is matter, really lies outside the realm of physics and belongs to that of metaphysics. That's, pathetic, but that's what we've come to expect from legacy science. They just can't get over their denial of the fact that their system is not all that. And if they just kind of admitted that they had a little bit of ignorance about their topic, they would be doing a lot better. But anyway, thanks for tuning in today, and have a